And now, I'd like to introduce McObject's Chief Operating Officer, Chris Marine.
Thank you, Ted. Hello, everyone, and thank you for joining us for our webinar, Real-Time Database Systems for Industrial Control. In a moment, McObject Sales Engineer Tim Sharp will start us off with an overview of the emerging data management needs of industrial control and automation applications. Next, McObject's Marketing Director Ted Kinney will present case studies of two companies that have used real-time off-the-shelf database systems to enhance control systems performance and reliability and reduce their time to market. After that, we'll have time for questions based on the presentation and also about database technology in general. You'll be able to submit questions using the Q&A window in the lower right-hand corner of your screen. We have a very interesting session for you today. The market provides various database systems to choose from with conflicting information regarding which are most appropriate to use in your real-time software. Our session is designed to help clarify those differences and to help you make the best decision for your development. McObject was founded 9 years ago with the unique goal of bringing to the market a highly optimized and reliable database system for in-memory usage, thus eliminating the need to build your own data management tools. Our founders, who at the time had more than 20 years of experience in database and embedded software fields, created eXtremeDB to meet the unique database needs of real-time embedded systems. The rapid adoption of eXtremeDB in the embedded systems proved the need for such a product. Since our inception, eXtremeDB has been used in applications including industrial control, networking and telecommunications, avionics, consumer electronics, and many other vertical solutions. This success has fueled McObject's growth with staff, customers, and offices throughout the world, and millions of applications that have shipped using our technology. If your embedded control or automation application requires real-time data management, we hope you gain information today that improves your project's results and invite you to contact us after the event with any additional questions. With that, I'd like to introduce our first speaker, Tim Sharp. Tim?
Thanks, Chris. Today I'm going to talk about industrial control and what challenges exist with respect to data management. So what is industrial control? In a nutshell, these are systems that are designed for gathering and storing information to monitor and control a variety of industrial processes. Because data plays such an important role in these systems, we can see that there's obviously many opportunities for data management. The types of control that we see today include SCADA, where control is centralized, DCS, where control is distributed, and systems that combine elements of both models. Industries that generally implement industrial control systems include building automation for climate control and managing energy usage, industrial processing plants such as oil, gas, chemical, and wastewater, power utilities for energy production, and manufacturing plants such as pharmaceuticals. Needless to say, the list could go on. Industrial control can be broken down into four main divisions. First is data management and can include raw data from sensors, instance variables, and data stored either in memory or persistently in a disk on a database. Next, there is communication, which is a network that connects all the various modules in the industrial control system and can either be wireless or wired and support a variety of protocols such as TCP/IP, BACnet, Zigbee, and a myriad of others. The business logic is the brains of the system and defines what actions should take place in response to specific events. For example, if a room is too hot, the AC should be turned on. And if an alarm is set off, appropriate action should take place. Finally, there is control. This is where the tire hits the road and can consist of a number of devices such as pressure actuators, temperature sensors, hygrometers, or light sensors. It should come as no surprise that all four areas are heavily interrelated and that decisions concerning one area are bound to affect the others. For example, if all business logic and data management are centralized in one location, then you might experience a higher amount of network traffic from sensor data. This will in turn affect the system latency or how quickly the system can respond to a particular event. Let's first take a look at a traditional SCADA installation. This type of system can be described as data gathering oriented or event driven. The control center and operators are at the center of its universe, and the remote equipment is merely there to collect data, though in reality it may also do a very complex process control. SCADA systems typically implement a distributed database, commonly referred to as a tag database. These databases contain data elements called tags, which represent a single point or output value monitored or controlled by the system. Depending on the size and complexity of the system, the number of tags or points in the database can range from the hundreds to the tens of thousands, and the resulting database can grow into the hundreds of gigabytes. There is a communication network connecting the various components of the system. Again, depending on the nature of the network and the number of sensors, the amount of data on the network can potentially have an adverse effect on the performance and responsiveness of the overall system. There is the business logic that monitors the system for events and alarms and controls the corresponding actions of the system. And finally, there are the sensors and actuators that are providing raw data and responding to events. A SCADA system often needs to get secure data and exercise control over potentially a slow and unreliable communications medium. And subsequently, it needs to maintain a database of last known good values for prompt operator display and control. In terms of data management, issues to consider are: is the database fault tolerant? Will the database scale to handle large amounts of data coming in from the field units? And finally, because potentially there can be a very large amount of data to store, will the database be able to scale to support very large databases? At the other extreme, there is a DCS, or distributed control system. These are dedicated systems used to control manufacturing processes that are continuous or batch-oriented, such as oil refining, petrochemicals, or pharmaceuticals. In this architecture, the business logic is embedded in the individual intelligent controllers that are distributed about your installation rather than being centralized in one location. And each controller may have its own database that can contain process data and a limited amount of history data. In addition, there may be an external database for storing event history that can be used for determining trends and patterns. And then there's the network which all the devices connect to, and in some cases, this may be a mesh network. And finally, there are the control devices providing raw data and responding to the alarms. Now, for the most part, these controller modules are defined by extremely constrained environments, such as limited memory, low power CPUs, limited persistent storage, flash memory, and possibly limited power availability due to using batteries. So what are some of the primary considerations that must be taken into account when considering a database in such an environment? First, a database should have an extremely small footprint. It should also exercise the CPU as little as possible to perform these database operations. If persistence is required, it should minimize the size of the database files, and because flash memory can degrade significantly over time, RAID operations should be as efficient as possible. It should be able to provide real-time performance, and it should minimize power consumption in the event and in the case of battery-powered devices. So to summarize, we see that there are multiple opportunities for the use of a database in an industrial control system, each with their own requirements and expectations. In all cases, performance and reliability are a must. Performance helps ensure real-time responsiveness, and it should be extremely reliable in that upgrading a device out in the field can be significantly more challenging than fixing a system in-house. It should support replication to provide high availability, thus scale to a large number of users, and it should scale to large databases. It might need to be optimized to work in constrained environments where resources are extremely limited, and it should provide some level of persistence either for recovery or have a flexible form factor where the database can be stored in memory and on disk. And finally, it should support a variety of programming interfaces such as Java or SQL. At this point, I'd like to introduce eXtremeDB and talk about how we address these challenges. So let's talk about performance and ask, why is an in-memory database faster than a disk-bound database? First of all, we need to understand that disk access is one of the few mechanical components of a computer system and suffers from the slowness of its mechanical parts. Its throughput is 100 megabytes per second compared to 5 gigabytes per second for RAM, and you can also expect to experience latencies on the order of 13 milliseconds for disk versus 10 nanoseconds for RAM. The difference in performance is several orders of magnitude. There is no comparison. Disk-bound databases recognize these limitations and so will do whatever is necessary to reduce I/O, trading off memory consumption and CPU cycles in order to accomplish this. Next, with a disk-bound database, data is transferred and copied extensively. As you can see from the diagram to the right, multiple copies of the data are created when an application makes a request against a disk-bound database. In fact, a simple update can involve 4 different copies and 6 transfers to move the data from the hard drive to the application and back again. And this is a simplified scenario that doesn't account for additional copies and transfers that are required for transaction logging. And finally, as I said earlier, in order to reduce I/O, disk-bound databases must spend extra CPU cycles managing its internal cache, which is not trivial considering that it must track dirty pages, among other things. In contrast, with an in-memory database, there are at most only 2 copies that are made that must travel between the application and the database via the database manager, and there are no CPU cycles wasted on maintaining an internal cache. The in-memory database is the cache. Next, indexing can play a key role in achieving better performance, and McObject addresses this by its support for a number of different indices. As expected, we support both a B tree and a hash index. Whereas a B tree search can be unique or not unique, a hash index is suitable for searches by equality only and is by definition unique. The R tree index is commonly used to speed spatial searches. For example, finding a rectangle that bounds this point, or finding all rectangles that overlap a particular rectangle. The Patricia tree is particularly useful for network and telecommunication systems. In contrast with a regular tree, the edges of a Patricia tree are labeled with a sequence of characters rather than a single character. This can be a string of characters or a bit string, such as integers or an IP address. And finally, the KD tree is a data structure for organizing points in a k-dimensional space. KD trees are a useful data structure for lookups that involve multidimensional searches. As to be expected, eXtremeDB is fully ACID compliant. If a database isn't ACID, it really isn't a database. ACID is an acronym which stands for Atomicity, Consistency, Isolation, and Durability. Atomicity guarantees that all operations against a database that occur within a transaction are successful as a unit or fail as a unit. Consistency ensures that the database remains in a consistent state before the start of the transaction and after the transaction is over. Isolation refers to the requirement that other operations can access or see the data in the intermediate state during a transaction. And finally, durability guarantees that once a transaction has been successfully committed, the transaction will persist and can't be undone. One way eXtremeDB supports durability is with transaction logging, which is used primarily for recovery. It provides for persistence by writing changes executed against a database in a transaction log file. Depending on the level of risk a system is able to handle, the transaction log file can be written to synchronously after each transaction so that no transactions are lost. Or the database can be configured to write to the transaction files asynchronously, either after a specified number of transactions, or periodically in fixed time intervals, or finally at the convenience at the operating system. For performance reasons, only a single write is done to the log file, regardless of the number of operations in the transaction, and when the log files are flushed to update the persistent backup image, again, only a single write is executed against the database image. Because of this, read performance is unaffected by transaction logging, and write performance far exceeds the write performance of traditional disk-bound databases. This is in contrast to a disk-bound relational database where multiple write operations may be needed in order to update a single record. Finally, because only a single write operation is ever done during a transaction logging, this reduces the wear and tear of your system when using flash as your persistent media. At this point, I'd like to take a few minutes and talk about McObject's approach to reliability. The term reliability is a highly fluid term, but it's most commonly used to refer to a tool doing its job as expected without defects or bugs. Having said that, remember, eXtremeDB was initially designed for the embedded device market, and as such, was expected to be highly reliable as a database. In other words, the systems that were depending on it could be confident that it would not fail due to defects. McObject has taken that philosophy one step further and decided that not only should itself be reliably free of defects, but that it should also actively contribute to the implementation of defect-free data management within the intended application. McObject has approached this idea from two angles. First, it implemented a revolutionary dynamic API interface that reflects the schema of the database. For example, if your schema contains a class or record called animal and a field called dog, you can expect to use APIs with signatures like animal new to create a new animal record, animal delete to delete the animal record, animal dog get to retrieve the dog attribute, and animal dog put to update the dog attribute. In this way, the developer knows as he's writing code what kind of data he should be passing to the API, resulting in fewer errors. This ease of use greatly accelerates the learning curve for the developer because the APIs are more intuitive and tied directly to the data they're handling. Next, by implementing API signatures that are coupled to the data types, the API are thus made type safe. If the wrong type of data is passed to the API, the error will be detected at compilation time. And we all know that catching compilation errors are far less expensive than finding runtime errors when your product has already been deployed out in the field. Most database APIs are based on void pointers, which enables them to be able to accept any kind of data structure. However, void pointers can be very dangerous to use. Void pointers don't check to see if you're passing the correct data and are thus one of the biggest reasons for database corruption. With EXtremeDB, we've eliminated all use of void pointers, and to this day, we have yet to experience a corrupted EXtremeDB database out in the field. Finally, we offer two versions of EXtremeDB, a release version and a debug version. The debug version includes numerous traps in the runtime code that can be selectively disabled during development to help optimize the application for performance, as well as to expose defects that might not otherwise get caught until after the product has been released. After the product has passed all verification tests, developers can generate the release version of the EXtremeDB runtime, thus removing the traps and internal checks. EXtremeDB supports replication for providing high availability of your data, and again, depending on the level of risk you're willing to assume, you can choose either synchronous or asynchronous replication. In our implementation of high availability, there is a master database that has read-write privileges and multiple replica databases that allow only read access. Synchronous replication is appropriate for systems that are unable to tolerate stale data on their network and ensures that the master and replica databases are identical at all times. EXtremeDB's synchronous time-cognizant two-phase commit provides for data consistency in a straightforward manner. After an update to the master database has been successfully committed, the updates are then sent to each of the replica databases. If the master doesn't hear back from the replica that it has successfully committed the transaction in a pre-configured amount of time, that replica is removed from further consideration, and in this way, predictability is enforced. Although synchronous replication ensures the highest level of data consistency between the master and the replicas, performance suffers because the application is blocked while waiting for the replicas to confirm that the transaction has been committed on their side. EXtremeDB's other replication strategy is a lazy asynchronous one-phase commit that, while sacrificing data consistency, enjoys higher throughput. The asynchronous one-phase commit is defined by the fact that, unlike the previous case, control is immediately returned to the application after the master database has successfully been updated, and updates are propagated to the replica databases as separate transactions. In both cases, EXtremeDB ensures fault tolerance and addresses the question, how can a RAM database survive the failure of software or hardware environment in which it operates? McObject's EXtremeDB 64 database provides real-time 64-bit processing to greatly accelerate sorting, retrieving, and analyzing of very large data stores. Compared to a traditional 32-bit processor, 64-bit technology approximately doubles the amount of data a CPU can handle per clock cycle and increases the amount of addressable memory from approximately 3 gigabytes to more than 4 petabytes. As an aside, EXtremeDB has been successfully tested with an in-memory database of 1.15 terabytes. This testing is described in detail in a white paper that is available on our website called McObject Breaks the In-Memory Database Boundaries. A number of our customers, specifically in the social networking, telecom, and financial markets, have implemented eXtremeDB 64 as a data accelerator or a front-end database cache to their enterprise databases, effectively sitting in front of their Oracle or SQL Server database. And finally, we recently introduced our new data relay technology as a key building block for building fast and flexible data sharing between real-time applications based on eXtremeDB and external systems such as an enterprise database. Essentially, it enables developers to search inside database transactions for changes that should be relayed or propagated and eliminates the CPU-intensive task of monitoring database activity. Another important tool for scalability is eXtremeDB's optional multi-version concurrency control transaction manager, or MVCC, which is available as an alternative to the pessimistic database locking of the original eXtremeDB transaction manager. With MVCC, each connection holds a subset of the database which is being modified and thus offers finer granularity of locking. Unlike the standard multiple read, single writer approach, which implements pessimistic locking, resulting in all or part of the database being unavailable, MVCC uses optimistic locking, which assumes that no other users are modifying the same record. For the most part, collisions are not a concern as the performance of memory ensures that transactions are extremely fast. On multi-core machines, MVCC can dramatically improve scalability and performance, especially in applications with on-disk or hybrid database storage where there are many tasks or processes concurrently modifying the database. By intelligently designing our core database functions, we have created an in-memory database system with an unbelievably small footprint of under 150K. This makes eXtremeDB a powerful enhancement to any intelligent device with resource-constrained environments. This footprint is possible because eXtremeDB was originally built to be pure in-memory and was thus streamlined to have smaller database files and use less memory. For example, the metadata in an eXtremeDB database can be as low as 15%, whereas with a traditional relational database, the metadata can be anywhere from 100% to 1,000% of the original data. In addition, because we don't need to support such things as a cache, remember we are the cache, or maintain multiple copies of the data, overall we consume less CPU cycles per operation done against the database. All this allows the developer to exploit low-cost CPUs, use less RAM, and overall consume less power, thus subsequently contributing to lowering the cost of your device. Because byte for byte, disk storage can cost less in memory and require less physical space, for small form factor devices with large storage requirements, disk storage may be a better solution than pure in-memory. For this reason, McObject introduced eXtremeDB Fusion. eXtremeDB Fusion extends McObject's core technology, enabling the developer to combine both database paradigms, in-memory and on-disk, in a single database instance. With Fusion, it's possible to specify one set of tables as transient, managed in memory, while choosing on-disk storage for other tables. The persistent database can be stored in one file to simplify maintenance, limit I/O, and reduce the size of the database, or it can be distributed across multiple disks, such as in a RAID system. The resulting embedded database system retains the strength of in-memory, yet leverages the potential cost savings and built-in durability of on-disk storage. And finally, eXtremeDB has support for multiple programming interfaces. The C-based native interface is our fastest, providing type-safe API with signatures based on the schema. The UDA, or Universal Database Access Interface, allows applications to bypass the native interface and use a predefined generic navigational API for database access. For organizations already using Java, eXtremeDB JNI delivers the speed of compiled C for performance-intensive database tasks with the convenience of using a familiar language. McObject's Extreme SQL Embedded Database Interface is a high-performance implementation of the SQL database programming language. eXtremeSQL is an ideal solution for application development in fields where real-time responsiveness is a must and SQL is the dominant database language. eXtremeSQL also has support for the Open Database Connectivity Standard, expanding eXtremeDB's ability to share data with systems ranging from mainframes to servers to desktop applications, and enabling development using open and familiar database technology. Next, I'd like to introduce Ted Kenny, Marketing Director of McObject. Ted recently interviewed two of our customers in the industrial control and automation field, prepared case studies showing how they use the off-the-shelf embedded database technology in their commercial applications.
Thanks, Tim. And for our first case study, I'd like to talk about a company called Baltic Information Systems, or BIS. They're a Lithuanian company that provides technology for safety at nuclear power plants. And BIS started an operation providing a monitoring and safety system that ran on OpenVMS using the OpenVMS System API to manage data in shared memory. The company determined that it wanted to create its own SCADA system for the nuclear industry, taking advantage of the technical strengths of Linux, which has emerged as a leading platform in the European markets that it serves. The result is called BISMARC, a universal process control and monitoring SCADA system that can be configured for almost any plant monitoring task. And perhaps it's easiest to understand BISMARC by looking at a field deployment. This slide represents BISMARC as it's currently used to monitor radioactive waste processing at the nuclear power plant in Smolensk in the Russian Federation. And here it runs 24/7, 365 days per year on 3 nodes, 2 operator nodes and 1 administrative node. BISMARC nodes can function as both client and server simultaneously. Client functions include data visualization and user interaction, while the server handles PLC data acquisition, data processing and analysis, and archiving. And the 3 BISMARC nodes in this installation are based on Debian Linux running on Contron industrial PCs, although the PCs could be any fast x86 compatible box. The BISMARC server monitors a constant flow of information from the PLCs. The PLCs, in turn, communicate with and control the plant machinery that processes the nuclear waste. In this installation, the PLCs come from RTP, a U.S. company, but in a different installation, the server could interface with other PLCs from another manufacturer, with the sensors themselves, with an OLE for process control server, a gateway machine, or with some other device. Now, in a BISMARC installation, there are 2 database systems. One's an external relational database that stores information on disk. And then within the server module on each node, eXtremeDB manages an in-memory tag database. Tim described the concept of a tag database earlier. Each tag, or point, represents a single input or output value that's monitored or controlled by the system. And these tags are processed in real time to support functions such as alarms and support for supervisory decision making. In the Smolensk installation, eXtremeDB manages approximately 10,000 tags in memory. Each point typically has static attributes like measurement units or warning or alarm thresholds, as well as real-time values that change along with the system state. Static information is stored in the external database. It's loaded when necessary into eXtremeDB, such as at system startup. The real-time values, on the other hand, come from the PLCs or from other devices and are managed in real time by eXtremeDB to support BISMARC's core tasks. And these real-time values are periodically flushed to the SQL database for archiving. Performance was a key embedded database requirement for the tag database. Each real-time value is updated at least 3 times per second, and eXtremeDB's in-memory processing handles this rate easily. eXtremeDB's native navigational API also contributed to performance, and indexes, particularly eXtremeDB's support for B-trees, helped to deliver the needed speed for the tag database. During the design phase, BIS did consider creating their own database, which probably would have used an in-memory data structures and a C language interface. But the engineers also recognized the challenges of this task, particularly the time and complexity that it would entail. And one engineer credits the use of eXtremeDB as an off-the-shelf database with trimming 6 programmer months from the development cycle. Finally, BIS sought portability in its embedded database. It may someday offer its solution on Windows or 64-bit Linux, and eXtremeDB, with its support for all major server and real-time operating systems, and its ability even to run without an operating system, helped to create a portable code base. Finally, here's a view of the BISMARC operator interface at the Smolensk radioactive waste treatment facility, showing the equipment and processes used in the transportation subsystem of the plant and populated with data that's managed in real time with eXtremeDB. Clearly, there's a lot going on the screen, which speaks to the complexity of the system. Diving into the details is beyond the scope of today's discussion, but you can see how system components are interconnected, and the interconnections imply shared data that's facilitated by eXtremeDB. The next case study looks at a highly distributed application with processing taking place on many resource-constrained nodes. Building automation systems can cut building operation costs, produce happier tenants, and result in a greener environmental footprint. New wireless technologies have brought about savings on both installation and maintenance. But large upfront costs for protocol integration and other software, the costs of dedicated hardware and integration services, have made the technology impractical for smaller jobs. A company called SCL Elements created its CAN2GO technology to eliminate these costs by dramatically decentralizing building control systems based on smart controllers that replace functions formerly found in the central server. As Tim mentioned before, a control system typically performs 4 essential functions, and in SCL's visualization of their market, here's how these functions occur in a traditional building automation system on different network levels or tiers. First, control over actual building systems like HVAC and lighting traditionally occurs at the field level, while communications is the responsibility of dedicated networking devices throughout the system, with protocol integration functions on the server. Intellectualization, the smarts of the system, traditionally resides on the server. Data management is at the server level with control variables stored in the field level controllers and some communications data in networking equipment. Note that with all these functions on different tiers and levels of the network, there's labor costs to integrate, and there's also a cost in terms of bandwidth. Network round trip occurs every time data travels from a sensor as an input to the central server and returns in the form of control instructions. CAN2GO's innovation is to gather these 4 functions on its smart controllers, where embedded software called the sharing kernel manages the collaboration between them. On the smart controller, a communicate embedded software module converts protocols is aware of other controllers and contains the network mapping. An intellectualized module implements the sharing kernel, and for programming incorporates the lightweight Lua scripting language with extensions created by SCL elements, including a real-time task scheduler that allows easier handling of time-based functions. Also on the controller, the Manage Data software module is based on the eXtremeDB in-memory database, and its task is to store, filter, and retrieve data ranging from control variables to routing data, history, and state information for use by the other modules. And finally on the controller, the control module has direct interaction with the outside world and applies user-selected control strategies such as neural networks. By replacing a server and networking devices with this controller, where software and communications functions are pre-integrated, a network based on these smart controllers can significantly lower building automation setup costs. Now let's look at the database needs on the Manage Data module. First, the footprint of a relational SQL database system, even one that's promoted as being embeddable, would likely overwhelm the local RAM and CPU resources. The performance of SQL, with its high level of abstraction and its cost-based optimizer that considers thousands or even hundreds of thousands of execution plans, likely could not deliver the predictably fast response time that's needed. In contrast, eXtremeDB's main memory storage delivered that performance. And as for resource constraints on the controller, eXtremeDB minimizes RAM and CPU demands, and its code size can be 150K or smaller, depending on the platform and on the options that are chosen. Meanwhile, it delivers real database features, and these include transactions that ensure data integrity, support for diverse database indexes, and a rich and type-safe C++ language API. And perhaps eXtremeDB's greatest advantage for the CAN2GO controllers was its track record. It's a proven database solution in embedded systems ranging from avionics to set-top boxes to nuclear waste processing. And this final slide shows a hypothetical deployment of CAN2GO in a multi-level building. The circles labeled DCM are the smart controllers, and those marked DE are sensors, actuators to interact with building systems. CAN2GO uses protocols that are appropriate to the particular sensors or actuators that are being used and also to the building environment. For example, it uses the N-Ocean protocol to communicate over short distances and to support low power or even no power devices. Zigbee is supported for wireless meshing and resiliency. CAN bus is also supported, and it provides a wired connection and is very useful in overcoming Faraday cage conditions that would block or attenuate wireless signals. And finally, Ethernet IP is supported, providing a window onto external networks and also allowing use of a browser-based administrative tool. Again, the protocols are integrated locally on the controllers themselves, and each smart controller includes an instance of the eXtremeDB in-memory database, which manages everything from temperature sensor values to ventilation control motor speeds to the spatial locations, network interfaces, and addresses for the various nodes in the system. And that wraps up our two case studies. I'd like to now turn to questions, take questions from the audience. You can type and submit your questions using the Q&A box on the lower right side of your control panel. Are there any questions from the audience? Okay, one question that's coming in is, you describe in-memory storage as providing the highest performance, but also talk about a database that combines in-memory and disk-based storage. How is the second one, combined storage, different from database caching?
I'll take that, Ted. With eXtremeDB, you can define in your schema two types of tables, a transient table that is held purely in memory, and persistent tables that are persisted to your hard drive. The transient tables being held in memory don't need a cache. Remember, we are the cache in this respect. For the persisted tables, you do have to define a cache, and this cache can either hold all or a subset of the persisted database, depending on how much memory you have. If the memory is not enough to hold your table, pages are swapped out of the cache using a least recently used algorithm. And in addition, you could actually use the in-memory tables as an intelligent cache, keeping and removing data as required. So there's a cache only required for the persisted tables, not for the transient tables.
All right, thank you. Any more questions from the audience? One that's come in is, you mentioned the possibility of your database system used on Linux and Windows. These are fine for servers and the desktop, but controllers and PLCs will use embedded OSs, proprietary OSs, or even no OS. What are the options for using a real-time database then?
We actually support a number of operating systems besides Windows and Linux. We support WinRiver's VxWorks, QNX Neutrino, Green Hills Integrity. These are the real-time operating systems, as well as a number of real-time Linux flavors. We also support other operating systems like Lynx OS. And in the case of no operating system, we do support bare bones motherboards. And if you have a proprietary operating system and not a common one, our database is quite easily portable to operating systems, so we would have no problem in that as well. So yeah, we do support a lot of operating systems besides Linux and Windows.
Are there some more questions? What is a SCADA database?
A SCADA database is generally a distributed database. It's also called a tag database, where the tags are individual points, input values that are monitored and executed upon by the system. Generally, the requirements for a SCADA database are that it has to be really fast or high performance to ensure real-time responsivity. It needs to be fault tolerant. It needs to include timestamping, and it should provide high availability. All these things we do support, and though we're not explicitly a SCADA database, we do have customers in this field who use this in this manner. So.
All right. We do have time for another question or two. Any more questions? One question has come in. Is your database hard real-time?
No, we're not a hard real-time database. And in fact, there are no hard real-time databases currently available on the market. However, we do support some aspects of real-time, such as notifications or triggers that enables the system to respond to changes in the database. And we are deterministic in the sense that we do provide a two-phase commit for high availability. This ensures predictability. So, and also, our high performance pretty much makes us near instantaneous because we're when you use the pure in memory. So, yeah, there are no real hard-time databases out there, but we try to implement some of the functionality that is defined as one.
All right. Are there any additional questions? Just wait for a moment. It looks like we've come to the end of our event today. If you do have additional questions, please feel free to contact us using the information provided on the screen, and we will get the information that you request. And we'd like to thank you for attending the webinar today. We hope you've gained a good understanding of how data management contributes to an industrial control project. And as we've seen, the features of a chosen database system and even the choice of whether to use an off-the-shelf database do have an impact on the resulting application's performance and predictability, and on the development project's cost and time requirements. I'd like to invite you all to visit our website for many excellent white papers, links to articles, and also replays of this and other webinars. This webinar should be available there in the next 48 hours. We will be holding follow-on sessions in the upcoming weeks and look forward to